Good afternoon, everyone. My name is Francesco Volpe, and my ambition and the ambition of Renaissance Fusion is as big as this big purple badge. If you have an equally big and equally ambitious yellow badge, let's talk after this presentation. I'm going to bring you to Destination Stellarator, and I'm going to show you that along the way, we can monetize on some deep technologies. We are recreating on Earth the energy of the stars, fusion energy, but doing so economically on Earth requires materials that are not to be found on Earth yet, and shapes not found on stars, because we cannot rely on humongous spheres held together by gravity. Instead, on Earth, we have to be more ingenious. This ingenious shape is a donut on which charged particles, ions and electrons, move. And this donut is distorted in such a way that particles, when they're moving up, they think they're moving up, they are in effect moving down. And the net result is that they don't move, they stay on the donut, they stay confined. And this is important for fusion, because if they stay confined long enough, sooner or later, statistically, they will fuse with each other. So heavy hydrogen, deuterium, and super heavy hydrogen, tritium, will fuse and will produce helium, as in balloons, and neutrons. Most of the energy is released in the form of neutrons. And the name of the game is to capture that heat from neutrons, transfer it to water, that becomes steam and moves turbines. Now, it's a lot of heat. We are recreating a star on Earth, after all, so there are issues in materials coping with these extreme heat fluxes, as well as materials generating the strong magnetic fields in optimal shapes. And we found these optimal materials in, respectively, high-temperature superconductors, liquid metals, and as optimal shapes, piecewise cylindrical donuts. Let me explain better. We build stellarators, which are the only steady-state fusion energy device, which is perfect for your power plant. If you want to put 1 gigawatt in the grid, you build a 1 gigawatt power plant. If instead your system is pulsed, let's say as a duty cycle of 50%, 1 gigawatt in the grid means a doubled investment, a 2 gigawatt power plant, and twice as expensive cost of electricity. So the Stellarator is perfect for these reasons, but it suffers from 3 challenges, and we are addressing all 3 of them thanks to these 2 materials and 1 shape. Stellarators tend to be large and expensive, but it's magnetic fusion. So with high temperature superconductors or HTS, we generate stronger fields and make these devices more compact and cost effective. They produce neutrons, they produce a lot of heat. We cope with them by means of layers of liquid metals surrounding the small star on Earth, capturing these neutrons, capturing this heat, minimizing maintenance. And they tend to be complex donuts, but we revolutionize this. We build our magnets on just cylinders. And this disrupts the manufacturing process of these magnets in the way shown in the next slide. So unlike competitors that when they build electromagnets have to wind tapes or cables many times, which is difficult for stellarators because of the complex shapes that you see here, Unlike what competitors do, which is reminiscent of complex 3-dimensional sculptures, we instead do something reminiscent of paintings or engravings. We deposit the superconducting material on large surfaces, for instance, cylinders. Then with a laser brush, we selectively remove narrow tracts of material. And the result are large printed circuits, superconducting printed circuits that can be manufactured in a gigafactory, shipped to your power plant assembly site, and mounted together as in a Lego, building quickly and cost effectively your power plant. This allows us to unify the advantage of the Stellarator, which is the simplicity of operation, one more time, stable and steady state, with the advantage of the tokamak, another type of donut of fusion device, which is simple to build. It's just a smooth donut indeed. So ours is simple to build and simple to operate, thanks to this idea of the wide high-temperature superconductor engraved on the large surfaces. Now, I promised some commercialization along the way of deep technologies into other markets, and here they are. The first one is that this requirement of fusion for large, powerful, and yet very accurate magnets is not unique to fusion. You have it in medical imaging, magnetic resonance imaging, in levitated trains, electric motors for electric vehicles, generators for wind turbines. So in all of these applications, indeed, you need powerful, precise magnets. With our technology, we can do that. What we need to change for these other products is just the pattern of the corrugation with the laser. But it's, in effect, the same product serving multiple markets, which, unlike fusion, for which we have to wait the middle of the 2030s, these other markets are here today, and society buys these products today. So we can commercialize as early as next year our HTS to these other markets and our liquid metals. Similarly to HTS, the requirements of coping with extreme heat flux and extreme neutron flux is not unique to fusion. You have extreme neutron flux in fission reactors, our cousins from conventional nuclear. You have extreme heat flux in aerospace, for instance, at the bottom of rockets, of the nozzles of rockets, or in space re-entry vehicles. And so liquid metals, with our liquid metal solutions, can serve these other markets and will serve these other markets already next year. Renaissance Fusion is located in Grenoble, France, but we are a very international company with 100 people from 24 different nationalities. I myself am Italian. We raised 60 million throughout our history, 5 years so far. And in these pictures, you see modeling of the stellarator, patterning of copper for the moment, the development of an experiment where we levitated, as I said, the liquid metal around the plasma. And we have more milestones ahead of us, even more exciting, including the next 3 that I'm going to show, for which we are fundraising as we speak. One is building the first wide HTS worldwide, and thus becoming the world's largest HTS manufacturer by volume. This will address a problem of shortage of HTS for fusion, because we are not the only company interested in this material, but there is a shortage, there is a lack of such artificially made material worldwide. It will allow us to meet the cost and the length requirements for instance, electricity distribution, because from this wide tape, we can cut it as a serpentine and make very, very long cables, ideal for electricity distribution, for a superconductive grid. And as I said, it will open markets only possible by wide HTS. The other milestone is to build a tabletop stellarator in copper, corrugated copper, the idea being that if we can generate accurate stellarator fields in copper in a reduced scale, there is no reason why it shouldn't work on a large scale with the HTS. And all of these milestones conspire together and blend together to converge into the ultimate milestone, which is a module of our stellarator. Our donut will consist of several cylinders connected to each other. And with this Series A, we will build one of such cylinders where we integrate the 3 technologies of the HTS, the liquid metal, and the stellarator magnetic field. And with this, I conclude. The name is Renaissance Fusion. My name is Francesco Volpe. I will be happy to talk with you. If not possible today, shoot me an email. Thank you for your attention.